everyone, welcome to GemChem. Now today's video is on atomic structure part 11 video, and here we will deal with Hunds rule for fully filled and half filled configuration and Hunds rule for spin multiplicity. So before starting, if you have not watched the previous videos on atomic structure, please do watch it. It will be helpful. I will give the link in the description box as well as the I button present above this video. Now let us start. Now, what is the Hunds rule for fully filled and half filled configuration? It states that half filled and fully filled configuration are more stable than the neighboring partially filled configuration. Thus, D5 is more stable than D4 and D6, whereas D10 configuration is more stable than D9. Now, using the concept of Hunds rule and the concept of exchange energy, which we have already seen and dealt with in our previous video, so we will try to answer this question. Now, if you have not watched the video for exchange energy calculation, please do watch it before watching this. It will be helpful. I will give the link in the description box as well as the I button present above. Now let us see what is the question. The question is given that the electronic configuration of 24 chromium is argon 4s1 3d5 and not 4s2 3d4. So the configuration is 3d5 and not 3d4. Why is it so? Though we know that first 4s shell gets filled completely and then we get 3d filled. So why this anomaly occurs? Basically, here the principle of Hunds rule comes into play. Now, first we need to calculate the exchange energy and show it. So, we know that for D5, right? So, where there is 5 electrons in each of the shells, we will obtain E exchange equal to 10K, that is E exchange becomes 5 minus 1 by 2 equals to here a K 10K. Whereas if it is D4, then for D4 the exchange energy is basically 6K, that is 4 into 3 by 2, that is 6K, right? So from this we see that exchange energy is more for this one, that is D5 configuration. So it is more stable. So we can tell that this is the explanation why electronic configuration of chromium is this one and not this one. Now the second question is like that only, that is 29 copper has a configuration of 4s1 3d10, whereas actually we should have obtained it as 4s2 3d9. But why this is so? We need to first calculate the exchange energy, E exchange energy. So for D9 we will get it as the E exchange energy to be as 10K for the D5 plus 6K for the D4. So we obtain it as 16K, whereas for D10 it is 10K for D5 plus 5 electrons, so 10K. So we see that 20K is coming. So it is more stable, right? So from the energy calculation, exchange energy calculation, it is evident that as we move from D9 to D10, the magnitude of exchange energy increases by 4K, right? 20 minus 16 gives 4K, and hence expected that D10 system should be more stable, but for D10 there is an additional pairing as compared to that in D9. This will account for the energization of D10 to a certain extent, but the exchange energy factor predominates here over the electron pairing, and so D10 being more stable than D9, it is for this reason that the configuration of copper is actually argon 4s1 3d10 and not argon 4s2 3d9. Why among D5 and D6 D5 is more stable? The D5 is more stable the reason for D5 being more stable is that though both have 10K values, we know previously, that is for D5 and D6, both have the same exchange energy, but still we find that this is more stable. So what is the reason? How we can justify the Hund's rule? Former is more stable because although they have the same magnitude of exchange energy, the fact that D6 there is an electron pairing. So since there is an electron pairing, there will be an electron-electron repulsion, hence this system will be energized. So for D5, the configuration is 1, 2, 3, 4, 5. But as for D6, one electron is increased, so here is a electron-electron repulsion which is coming into play. So as a result of which this D6 configuration gets destabilized. So D5 is predominant. Now we see Hund's rule of spin multiplicity, right? So for a given system Pn, Dn, Fn, the configuration with maximum spin multiplicity will be most stable. So how we can justify it? Let's do for D4 configuration. Let's start with D4 configuration. So for the first case, if we take D4 configuration, now if it is our d orbital, now the electrons will come for this one. This is the minimum case which we know. So for this, the S is 4 into half, that is 4 by 2, which is equals to 2. So what will be the spin multiplicity? Spin multiplicity is 2s plus 1, right? So it will be 5. And what will be the E exchange energy? It will be 4 minus 1 by 2, and it comes to be as, and there is a K, comes to be as 6K. Whereas if we take a second configuration, which we can take, there is another option 1, 1. So we can take 3 in up direction and 1 in down direction. So spin will be here 3 into half minus half, which will be equal to 1. So spin multiplicity in this case will be coming to be as 3, and the E exchange energy will be 3 into 3 minus 1 by 2 equal plus 1 into 1 minus 1 by 2K whole, right? So the value comes to be as 3K. Similarly, for the third configuration, we can write it as this one. If we take another configuration as this, 1, 2, 3, 4, 1, 2 up, 2 down, right? So in that case, spin equals to 0. So 2s plus 1 is also equals to 1. So E exchange becomes to be as 2 minus 1 K by 2 plus 2 minus 1 K by 2, which comes to be as 2K. So we can see as spin multiplicity is decreasing, the value of E exchange is also decreasing, right? For this case, it is the least when spin multiplicity is 1, that is least value. Thus the configuration with the maximum spin multiplicity is most stable since the corresponding total spin is highest. This in turn accounts for the maximum exchange energy. Thus the Hund's rule of spin multiplicity is an exchange energy principle. So this was the formal ending of the atomic structure videos, and hope this series was helpful to you. So thank you for watching. Do not forget to like, share, subscribe and comment.